So today I want to talk about another programming language, Postscript. And the idea here is not so much that I think you will program very much in your life in Postscript or something. The idea is more for you to give you the possibility to understand how an interpreter works internally and what are the minimum requirements on a programming language that, for example, is capable of executing recursiveness, also recursive function calls. So yeah, this is the idea of this class today, and I hope you enjoy it. Okay, let's go. Postscript is, as mentioned, is a stack language, so it uses basically two stacks, and we later see this has some implications on the syntax that is essentially very different from the syntaxes of Python or C or C++ or any other modern programming language. As I mentioned before, it's inherited from Force, an old from the 1960s programming language, interpreted language, one of the first interpreted languages ever. And yeah, let's have a look into how it works. Okay, first of all, yeah, I mentioned this already. John Warnock developed Postscript in 1982. Initially, he developed a predecessor of Postscript at the Xerox Research Institute in Xerox Park. Xerox is the Xerox Park Research Institute at Palo Alto. Is very famous also for other inventions. Maybe part of this course could be that we also watch the ultimate demo film from 1960 something, where they first demoed inventions like mouse pointers and cut and paste and these kind of things that were basically what is our everyday work process working with computers had been demoed at this time. This has also been developed at Xerox Park at this time. Yeah, and one of the workers there was John Warnock, and he developed the predecessor of Postscript, or in Postscript later, as a page description language. Yeah, here it's written again. Postscript interprets this predecessor that had been developed at Xerox. And as I said, Postscript is based on Force. Yeah, and he found then Adobe. Everybody now familiar with Adobe. Adobe now is a big software company in California producing things like Photoshop. Before it was also famous for Flash, a very common plugin on basically all browsers, without which you couldn't use the internet anymore for a while. But on the other hand, it was very error prone, so it vanished and is now replaced by features of HTML5. So apart from that, Adobe is also famous for the Postscript successor, PDF, the portable document format. And one important difference between Postscript and PDF is that, different from Postscript, PDF is not a complete programming language anymore. And this has good reasons, because the feature that Postscript is actually a programming language makes it also very prone to malicious attacks. So PDF has a reduced feature set in order to become safer. This is basically it. Yeah. So below you see a picture of him, John Warwick. Okay, what was Postscript made for is for, at that time, very advanced computer system, not the everyday computer. It handled the communication between the computer and the printer. before Postscript times, the communication process between the computer and the printer was very hardware dependent. In other words, the computer need to have a very specific driver system, like a software that was made exactly for this particular printer hardware and had to be placed every time the printer was exchanged. And this software basically described, if in the case of graphics, for example, described every pixel on the paper and transferred the color of each of these pixels on via a network or whatever the connection was, maybe a Centronics interface, a parallel interface at that time. And basically then the page was described in that way. And the next printer maybe had a different resolution, and that means that the hardware and everything that the software on the computer and everything that related to this particular printing software had to be replaced or updated or exchanged in some way. And the principal idea of this Postscript is now that it goes to the next level of abstraction. So it basically describes the page in form of a computer program, where it basically says, okay, there should be a circle with this and this diameter, and there should be a line, and there should be a text with this font, and so on. Then this information is transferred to the printer, and the printer then calculates out of this description what should be the value of each of the pixels that should be printed then, and then prints this out. So this requires, of course, a bigger hardware capability. You need to have a CPU and some pre-programmed software on the printer too, and this came then, of course, from Adobe, or was at least licensed by Adobe. But the advantage was also that the amount of communication load between the computer and the printer could be significantly reduced in this way. Yeah, so this was the advantage then. Okay, how does Postscript work? And as I said already, this is inherited from features from FORS. And the most important feature is for users is that it uses what is called the inverse Polish notation. So maybe in a modern programming language you would write here 5 plus 5, and then 5 plus 5 is equal to A or something, or A is equal to 5 plus 5. In Postscript it's written like that, 5, 5, add. And what is happening there is that that internally Postscript has something what is called a stack. Basically a stack is a pile of things, and you put things on top of each other. When you write to the stack and when you read from the stack, you take the things from the top of the stack. So this is a last in, first out kind of memory type, if you want. And so we can imagine here, for example, we have an example for a stack. We have here a lot of numbers on the stack, and then we have at the end the command add, so add these two numbers. What is meant there is that the numbers 4 and 12 should be added on that, so the numbers 4 and 12 that are on the top of the stack, you have to imagine this, the top of the stack, should be added, and after this operation is executed, we have then after that on the stack 1, 4, 10, 12, 18, 16. So the lower items on the stack, they just remain the same, and just the top two numbers are replaced then with the result of this add operation. So the stack is of course a very essential feature there. Yeah, here is something like a hello world application that I just copy here from Wikipedia. Basically this is like something like a magic magic code to show the operating system. This is a Postscript file, and then here we select the font. Of course what is the font is a particular very important information for a language that is particularly made for printers or courier. And then the size is also set, and then we have here this instruction, this Postscript select font, and then we move basically something like a cursor to some position on the page, and then the text should be shown. And at the end, there's an instruction to start the rendering process of this whatever has been written before. So this means from this point the page is then printed with all the information that had been set up before, and then after that what follows comes to the next page. Okay, yeah, let's go to an instruction or a little program that draws a line. Yeah, if you want to call this a picture, you could also call this a picture. So here, of course, again, this magic number or the intro for Postscript, and then we say move the cursor to the position 100, 100. Oh no, this means translate the coordinate system by 100 and 100 units. X should be translated and Y should be translated. This translates the origin of the coordinate system. Then we have to move to one certain position, and then we make a line between the first position and the second position, and this is this line 2 instruction. So this means go from the current position of the cursor to this position 100, 100, and as a result we will see here a line that goes from 0, 0 to 100, 100. Then here we have the stroke instruction. This means the line should be executed, and at the end again we have show page. And if we cut and paste this little program into a file in our editor and save it as a something.ps file, and we have the appropriate software to show Postscript, then we will see a line like this. Obviously Postscript is an interpreter language. Yeah, nothing is compiled here, everything is executed line by line, and we need to have this Postscript software always installed if we want to see the result of our Postscript program. Okay, this is an example for loops. What we want to do is we want to produce this kind of a extended stop sign, not with 8 corners but actually with 10 corners. So we set here first a color. Obviously everything here is red, RGB. This set RGB color. So the first argument is red, green and blue. Red is 1, green is 0 and blue is also 0. Then we translate again the coordinate system. We move to a certain position, and then here we have a loop, and the body of the loop, similar to C, is set into coordinate brackets. So basically this is some kind of a sub stack of items that should be executed every time the loop is executed. First argument to this, so the loop instruction is itself repeat. It takes 2 arguments. First argument is how many times this loop should be executed. Here in this case 36 times, which is too many times, but nevertheless 36 is okay. Probably it would be enough to have just 10 times here. And then we have here 100, 100 line 2, and then we have here 30 rotate. This rotates the coordinate system by 30 degrees every time. And then we have here the closing bracket for the repeat function, and at the end we have here stroke and show page. So this will result in this empty stop sign, if you want, with a white center. Maybe remember stop signs, they look more like that. If you want to have something like that, we have to replace the stroke instruction with the fill instruction. Yeah, we can replace stroke with fill here, and if we do that, we get the result. This result, then the content of this polygon is not is filled up with this particular color that is our color here. Okay, we can also define own functions. That's also a very interesting feature of Postscript and Force. So in Postscript it works like this. We introduce here a new name that is, okay, in this case we just, first of all, in Postscript it doesn't make a difference if we define here a variable or we define a function. Basically we assign here a name to some content, and at the end we have the keyword def that defines this function. So if, for example, if you want to assign the variable a with the value 50, we have to go this way. We have here /a. This introduces this a to Postscript, says this a is a new thing, and then we have to here say 50. So this would be the argument with which this a should be assigned. Basically in C we would write like a is equal to 50, and here we say /a 50 def, and this defines a to be 50, and later we can use then this a instead of 50. Also we can define whole functions. Here, for example, we say triangle. So this is a new word introduced into a new function name or a new variable name introduced to Postscript by using this / here, and then we have here the coordinate brackets that indicate everything what should belong to this triangle function. Yeah, so all these lines here belong to the triangle function. At the end we say def, basically saying every time this triangle is used, what is actually done is these lines are added into the program, and we see this would be instructions that belong to a closed, to a filled up triangle with the coordinate point 0, 0, 0, 50 and 50, 50. We need to mention here a few instructions in Postscript that do stack operations. For example, we have here this dup operation, and what this dup operation is doing is basically doubling the last item on the stack. So for example, if we have these numbers on the stack and the last one is a 12, the 12 is doubled. We can also exchange the last two numbers on the stack in Postscript. So maybe we have here 4, 12, then if we exchange it after that, this will be the 12. So the last item will be, before the last item was the 12, and the one before that was the 4, and after exchange the last item will be the 4 and the one before will be 12. Also there's a pop instruction, basically make the last item vanish on the stack. And we have also count instruction, just yeah, we can count here the items that are currently on the stack. So here would be 8 items on the stack, and as a result of this count operation we will have an 8 on the top of the stack because there are 8 items. Okay, maybe come back to the Fibonacci numbers. Already in the beginning of the introduction to programming course, we learned basically 2 fundamental ways to program things like Fibonacci numbers or factorials. One is the iterative way. Basically, if we do Fibonacci numbers, we count from the first 2 Fibonacci numbers to the nth Fibonacci number, and we go through all of these items and basically calculate the next one inside a loop. And also, of course, we can do this in terms of a Postscript program on the stack. So basically, we have here the first 2 Fibonacci numbers in the beginning on the stack, and then we have here a loop over n iterations when we want to have the nth Fibonacci number. And then we have inside the loop where we define a variable b with these instructions. Basically, this variable b is then the last item on the stack. We have to imagine, for example, in the first iteration we have here the 1 on the stack, and then we say the 1 should be equal to b. The normal syntax for a definition is /b 1 def, But here the syntax would be 1/b def. This would give an error. So we need to exchange first the last two items on the stack. So then we have /b 1 def. So this defines b to be 1. And then the same thing happens here with a. Takes in the first iteration takes this one. And then what we can do inside the one iteration of the loop, we say on the stack should now be ab. It would be again these two ones, and then we say a, b, add. Yeah, and we add then these two numbers. So after in the first iteration of this loop, we have then 1, 1, 2 on the stack, and then we go to the next iteration of the loop. B becomes then the 2 that is here, and a becomes 1, and then we have 1. The original one stays the same. Then we have here the 1 and the 2, and then 1 plus 2 as a last item on the stack, and so on and so on. And if we do this so and so many times, maybe 10 times, then we have here 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and 89 on the stack. And these are, of course, the Fibonacci numbers. Demo how what Postscript basically, or a language, programming language like that, an interpreter language like that, internally thinks. We see here several lines. First of all, this is the original program. That was this Fibonacci program from the last slide, and the interpreter works through this program step by step. So the red number here is where the interpreter is right now. He's in the very beginning and executing this one. When he executes this one, there's a data stack. That is basically this kind of memory that is last in, first out type memory. So here we see this one reappear in the data stack. Then we have one, what is here called execution pipe. This is still empty. This is basically internal modifications of this program while this program is running. So there are some changes happening due to the nature of these instructions. We will see later how it works. And then as a last line we see defined variables, so assignments, meanings, interpretations of names that come from these definitions. Yeah, this is the idea here. Okay, let's go here through this program. This is the Fibonacci program. If you look carefully, yeah, we have here 1, 1, 5. Here only 5 iterations because else it's hard to understand for a human. Then we have here the variable definition. So in Python this looks like /b. Here it's a and b. Then here's this exchange instruction, and here the def instruction. So basically we define here b initially. So this 5 is coming from this loop instruction, what is the repeat instruction in Python, Postscript in Postscript, so this 5 disappears, and then what is on the top of the stack is this 1 here, and this is then defined as b in this moment, and then you'll see that what is before in the stack is then defined as a. And then what happens afterwards is that A and B are put back to the stack, and then A and B, and then ADD. Let's go through that. First we go through this loop. How this loop is done here is, we will see how this loop is done. Just, you see here now the program goes to the second item. We go here to the second item of the program, and the data stack is updated. So here the data stack is updated with the 5 iterations. We want to do 5 iterations. Then the body of this loop is uploaded. So we see this is an additional list here in this Python program. Okay, and then we see this loop is interpreted. Initially this is a loop of 5 items. This is transferred here into a loop with 4 items. This is this part here. And then one part is taken out. So initially it was a loop with 5 items. It is transferred into a loop with 4 items. And then we have here as additional thing one iteration of this loop, and then we have a run instruction at the end. Yeah. Okay, and we go one step further. We see here then this n is put into the execution pipe. This is what this run instruction is doing. We go then to the next item of the loop. The loop is, instead of having a loop with 4 iterations, we have now a loop with 3 iterations, and at the end we have one time this the content of the loop with the run instruction. As a result, we have then this longer execution pipe, basically 2 iterations of the loop in the execution pipe, and so on. We see this happening with one loop with 1 iteration, and then we have finished. Basically everything is then, all the loop iterations are basically a long line of instructions in the execution pipe. And then what has to happen is that this execution pipe is executed item by item by item. And this is happening now. So we are here, then see the next instruction here is the def instruction. So this will be then on the top of the data stack. And what we have then is then the new variable b should be assigned with the value 1. And we see here after that the variable value b becomes 1. And the same thing happens with a. Next instruction is def. So after that we have these 2 variables defined here, a and b. And the data stack is empty in this moment. Out of this data stack we made empty data stack. And now we see here what follows: A, B, A, B, ADD. Yeah, so this is the situation before the ADD instruction. So we have here 1, 1, 1, 1. ADD will add the last 2 numbers here. See, there's a 2. And now we will define again B and A. It is no problem in Postscript to override old definitions. If the variable name is the same, you'll see the old name of B will be, the old value of B will replace with a new value after the following def instruction. So now B is 1, and now after we execute the next def instruction, B is 2 actually. And also A is reassigned, but A stays the same. And what follows is we fill up the stack again. Okay, so this happens now after we executed the last ADD instruction. So now we have on the stack 1, 1, 2, 3. Yeah, we see already it works. We define again B. B becomes 3, and A becomes 2, and fill up the stack again. Okay, now this is before ADD, so the last 2 items will be added. Okay, we have here 5. Find B again. And so on and so on. You see, what we see here that what emerges is the Fibonacci numbers on the stack, starting from the lowest Fibonacci numbers on the bottom, and then on the top the highest Fibonacci numbers. And at the end we have this here 1, 1, 2, 3, 5, 8, and 13. So let's, if we look back to the program says, okay, we have here the 2 first Fibonacci numbers, 1, 1, and then the program calculates out of that the 5 following Fibonacci number, so 2, 3, 5, 8, and 13. Also define a factorial function with a loop. So here is this little program, and that would be the output of this program. Just in a moment we can see how this works during runtime. Program in the loop version executed with the same tool that I used before. We see here the program, then the internal data stack of the interpreter. I should say these data stacks, they exist also, of course, in C programs during the execution of C. And then here we have the execution pipe, and here the variable definitions. Okay, we go here, so the program here is the 5 iterations. We want to repeat 5 times this part here. And then this is how this is internally processed. Out of the 5 iterations loop, we make a 4 iterations loop and 1 time executing in addition the code. And then we make a 3 and 2 and so on. In the end we have all these things here in this execution pipe, same as before. And then we start to processing this long string. We see here already A is defined with the value 1. We add 1 plus 1. And we define now A with this new value. A becomes 2. Okay. Next iteration, we define A with 3. Okay, now I pushed off, but then we multiply basically 2 with the value of A, so the result is 6. Now we have, it's an intermediate value 4 on the stack, but it's just to define A now, newly, and we get here A is 4 now. Now what is done, we duplicate the last value on the stack. So we have here now 2 6s. We multiply the 6 with the content of A. The result is of course 24. And then we put A on the stack and 1. And then we add here these things together and define then this as a new value of A. So A is equal to 5. We duplicate the last item on the stack. We multiply it with A. And finish as a last item. We have here the ID of this factorial on the stack. Okay, so we have here then factorial 0, factorial 1, factorial 2, 3, 4, 5, and as a last item we have the ID of this last factorial on the stack. Okay, but of course a nice feature of Postscript and Forth is that this is one of, or the simplest programming language that allow recursive definitions of functions. Let's have a look how that might work. Okay, here we see an example for a recursive definition of a factorial in Postscript. Yeah, this is how a factorial function would look like. We define here factorial, and you see already just from looking at it, inside the factorial function, the function is calling itself. So in principle, we see already the idea is a similar one to how we would maybe define factorial in C, how we learned that. Yeah, let's have a closer look. We know recurrent function definition always depend on a stopping condition, and maybe remember in C it would read like something: if the argument is larger than 1, return 1, or something like that. Here we have something similar. Here we say duplicate the top of the current stack and check if this is greater than 1. This is basically what this means. So if we execute this, this is basically checking if the top of the stack is greater than 1. If this is the case, the top of the stack is then a Boolean expression, and this Boolean expression would be true if actually the top of the stack is greater than 1. If not, this would be false. And this has to be read in combination with the if statement here. Again, we have the inverse Polish notation also for if statements. So the if statement takes as a first argument the condition, and as a second argument here in the bracket what should be executed if the condition is fulfilled. So here we see what should be executed if the condition is fulfilled. So we take again the top, duplicate the top of the stack, we subtract 1 from that, and then we say this number that is now in the stack, that should be again operated together with the factorial function and multiplied with the result of that. So in other words, we called here factorial maybe with one number n, and here we call factorial with n minus 1 if n is greater than 1. Yeah, and this is how we define here factorial. Let's have a look how this is done in the interpreter. Factorial program in this Python version of the Postscript interpreter. Yeah, here's the definition of the factorial loaded as a, yeah, we see here this program is basically some set of nested lists. On top is the program itself, and then here inside covered is the body of the if statement, and that is again nested in the function definition of the factorial. So this is how this program is stored. In this case, we have the data stack. Initially data stack is empty. We have the execution pipe is also empty, and then here we have the variable definitions, and now we start the program. We go through first instruction. We define this, if you want, variable factorial. In Postscript, variables are treated in the same way as function definitions. You see, after we have executed that part, the factorial is a variable that is handled like a list of instructions, a nested list of instructions. So after we have defined factorial, we put the value 5 on the stack, and afterwards factorial, and this is immediately replaced with the content of it. You see here, this is the list. That's basically according to this function definition here. We go on. It goes maybe through the first. So here's a run statement. This means we go here to the first instruction of the body of the function. And we have here this duplicate instruction, and that duplicates the 5. We check if 5 is greater than 1. We get here true. So the body of the if statement will be executed. And now we duplicate again. Then subtract, yeah, 1. And next instruction is again the factorial. So this means, yeah, we replace here just the variable name factorial with this whole list. So that's why we have this in the data stack. And remember, after the factorial, what followed in the execution pipe was this multiply. This still has to wait here. Yeah. We go on. We have now 4. We duplicate again. We check if the 4 is greater than 1. Of course, the 4 is greater than 1. We come now to the if statement. If statement is, of course, has to be executed. So we have here run. And then we come here, the next duplicate, we have to subtract 1 of the duplication, so we have here 3. Next thing is we execute the factorial. This means we replace this statement here with this whole list and say this needs to be executed. See also here the last multiply has to wait. We have here now 2 multiplies at the end. Yeah, let's go to the next recursive iteration and so on. Okay, now we are in the one before the last iteration. So 2 is still greater than 1, so we execute that. Okay, now we have on the stack 5, 4, 3, 2, 1. We call factorial one more time. Duplicate. So we have 2 1s here. We compare if the 1 is greater than 1. This of course then false. So this means this body here is not, this list here that belongs to the if statement is not executed. Yeah, just in this moment. And now we are in this situation that what we have on the data stack is 5 by the numbers 5, 4, 3, 2, 1. And in the execution pipe we have 4 multiplications. So we will multiply the 2 with the 1. This is 2. Then we multiply the 3 with the 2. And then we multiply the 4 with 6. And we multiply 24 with 5. And what we get here is a factorial of 5. Of Postscript in combination with recursion is that it's very useful to depict fractals. Yeah, what are fractals? I have here a collection of these these items of fractals. Maybe start with this here. This was invented by a Swedish mathematician. Here's his picture. His name is Koch, and he invented the Koch curve that looks or resembles an ice crystal. And how this Koch curve is constructed is that we start with a straight line between some values, maybe here x is 0 and x is 1, and then we take the middle part of this line out and replace this middle part with the upper line of a triangle. And then we have 4 segments. We have the segment 1, 2, 3, 4. And what we can do then is in each of these segments we can again replace the middle part with the upper silhouette of a triangle. And then we have how many segments we have? 1, 2, 3, 4, 5, 6, 7, 8. The 4 times 4, so 16 segments. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, yeah? And if we do this again, then we have 16 times 4, that would be 64 separate segments, and so on. The interesting thing is, if we do this infinitely many times, we will find out that the length of the curves becomes infinitely long. Initially the length is 1 before we do any of this takeout operations, and then after we do this operation one time, it's 4 divided by 3. If we do this 2 times, it's 4 divided by 3 square, yeah, and so on. So 4 divided by 3 exponent n. And if it's infinitely often, then this curve will become infinitely long between these 2 points. Yeah, you see here also other types of fractals. Here is the Mandelbrot set invented by Benoit Mandelbrot. Another example is the Sierpinski carpet, invented by a Polish mathematician. And then we have also the so-called Hofstadter butterfly that originates from some consideration about in a solid state physical system. And all these structures, they have very interesting features, but it's maybe a little bit too far-fetched to talk about all of these things. What we want to do is now we start maybe with the Koch curve, and we want to depict the Koch curve in terms of a recurrent function definition in Postscript. So this example is here. This is the definition of the Koch curve. We see here, yeah, there's a new word introduced, /Koch, and here's the corresponding define statement. And we see also here how this is used. We should use this Koch function together with a negative integer argument. So here we see if we use Koch with the argument -1, then we see that yeah, we take out the middle segment of a straight line and replace it with the upward part of the triangle. If we use Koch with a -2, then we do this replacement operation 2 times. So we see also for all of these segments we have the replacement, and so on and so on. And there we can approach the final Koch curve, where this should be actually -infinity, which is not, of course, feasible in a computer program, but we can approach it. You can choose a higher number and a higher number. We'll see that then at the end this Koch curve doesn't change so much anymore in the depiction. So we can assume the limit will be very similar to what we can achieve maybe here with the argument -10 or something like that. Okay, let's try out the Koch curve in our sample program. And here in our demo Python Postscript emulator, if you want, it's a little bit modified because the graphics here works different from the original Postscript graphics. Here an implementation of the school program Turtle is used. So we have here these instructions: pen up, pen down, and forward and turn. So this is good enough for us right now. So we define here this Koch curve and we check basically if our level is greater than 0 right now or not. If it's not greater than 0, then we call here this Koch curve with decrement 1. So we don't use your negative number, we use your positive numbers. So if it's greater than 1, we subtract 1 from the current value of the stack and execute the Koch curve 4 times inside this segment, and if the level is 1, we just draw a straight line. Maybe also it should be mentioned we use here a scale statement. That means we can set the scale, what is 1 unit in our coordinate system. So this is also implemented here in this demo Postscript version. Okay, let's have a look how this program works, and we see also the graphics. Okay, so here we are. Before actual Koch curve is executed, we move the cursor to an appropriate position. This is here the turtle from the turtle program, if you want. Okay, yeah, so we are here now. We set the pen down again, so we will see a line. And now we go through the definition of the Koch curve. You see here Koch curve is defined, also scale is defined. It's a variable. Okay, here the Koch curve is executed with a level 4. So you see we go already many steps before we reach the level of drawing something. Go down with the scale. Okay, maybe I just show it here now, like as it looks like in this level. Yeah, we see here this Koch curve is drawn, but it is maybe better if we first show it with the level 1 or with the level 0, yeah? So that would be just, of course, a straight line. Here we are again. Okay, there's nothing shown. Let's try it with the level 1. Yeah, so we go through the steps here. Move the cursor to the right position. define here the Koch curve, the function, and then we execute it with the level 1. And we come immediately to this if statement here of the Koch curve, where it's checked if the top of the stack is greater than 1. In this case it's already false. So what we do in this case is we go to the alternative, and that is we just draw a straight line. This is what it should happen here. Okay. And then to remove the top argument, there's a pop statement. Don't do anything. Just remove that the stack is empty right now. Okay, so this will be with the argument 1. We just draw a straight line. Let's try then the argument 2. Yeah, here we have this program one more time. So we have here, if we go with the argument 1, then this part is not executed. We just go to the second part where we basically multiply the total length with the scale that we are right now and move so many pixels forward. If we have Koch with the argument 2, then we go here one recursive iteration through this part here, where the Koch curve is executed 4 times internally, and we see here the scale variable is reduced by a factor 3. And we see we turn here -60, 120 and -60, and execute basically 4 times this statement, but with the reduced scale. Let's have a look how that works. Again, the preparatory steps. Defining the Koch curve. Okay, we go through the first if statement. Okay, now we see the Koch curve is now called with the argument 1, like before. Just the scale is reduced to 1/3. So, and then the first if statement is false, but the second one is true, and this means we move 1/3 of the length. Okay, and then we come back to the previous level, to the initial call of the Koch curve with the argument 2, but we rotate, we turn 60 degrees now, and go down to the level 1 again, where we execute the next line segment, 7 here, rotating 120 degrees, executing the next line segment. And we are here, and finish. So next, let's go to the next step. We call now Koch on the 3rd level. Yeah, maybe go through this a little bit faster. Go down 2 levels, and then we execute the first line segment. And here we are. Okay. Okay, thank you very much. I wish you a happy Monday evening. See you soon. Bye.